Yeah.
So not easy. And she will give this lectures on neutrino cosmology, which is also very interesting topic.
Okay, so I'm telling you about neutrinos and cosmology, and I just noticed that this one looks kind of dead. I was wondering what that meant. Anyway, so the idea of this series of 3 lectures on neutrino cosmologies is that I'm just going to tell you about how neutrinos fit into this grand scheme of things. So this here is obviously this history of the universe schematic, and neutrinos play a role in practically every stage. Okay, so the way I'm going to do it is as follows. I'm going to split the 3 lectures into 2 halves. Not a very good way to split things, but so that's the way it is. And in the first part, I will tell you about neutrinos in homogeneous cosmology. So I will start with like a kind of basic review of cosmology, the hot universe, how a neutrino background fits in. I'll tell you about precision CNUB as well. And in part 2, which will mostly be tomorrow and the third lecture, I will tell you about neutrinos in homogeneous cosmology, in particular things like neutrino masses and how we can probe non-standard interactions. So, so roughly what it means is that today I'll just be talking about how how we describe the homogeneous and isotropic universe, the hot universe's early times, and the inhomogeneous universe that I will describe in lecture 2 and lecture 3 would belong here in the low redshift universe. A few useful references that you can find. There's these days a dedicated textbook called Neutrino Cosmology, written by some of our friends here. There are also a lot of lecture notes around, which are really cosmology lecture notes. Baumann has a lot of cosmology lecture notes in various different versions, different courses he taught. There are also a couple of lecture notes here by Seljak and Hu for those of you who want to dig deeper into how to describe perturbations. And also a couple of reviews that you can find on arXiv quite easily. Okay, so let's start with part 1 on homogeneous cosmology. Okay, so this is the concordance flat lambda CNN model, which I guess most of you have seen, come across at some point. And it's usually presented in this way in terms of 2 pies. So one here is a pie that describes the energy content of the universe today. And you can see that most of it is dark energy, and dark matter is 25%, and there's some atoms and that. And if you dial the clock back 13.4 billion years to the time of what we call photon decoupling, you also see this different kind of pie, which depicts energy content at that time in the early universe, where most of the stuff was dark matter. And you also see some neutrinos, and of course photons, which is the CMB, and atoms. Okay, so when we come up with these pies, the basis for even coming up with these energy distributions is what we call FLRW cosmology. So FLRW stands for Freeman, Lemaitre, Robertson, Walker, 4 people who came up with the idea of describing our present universe at different times. And the basic principle behind that model is the cosmological principle, which states that our universe is spatially homogeneous and isotropic on sufficiently large length scales. So another way to put it is that we're not very special at all. Okay? Now, homogeneous and isotropic sound like the same thing, but they're not. Homogeneous means same everywhere, whereas isotropic means the same in all directions. So if you look at these 3 pictures over here, this universe is isotropic, kind of the same in every direction, but clearly it's not homogeneous. This one here, on the other hand, is homogeneous, but not isotropic, because all my planes are flying in one direction. And the last universe here, the one that looks like white noise, is the one that is homogeneous and isotropic. Now, the third condition is that this idea of homogeneity and isotropy is only true on sufficiently large scales. And what we mean by sufficiently large is essentially anything that's larger than about 100 megaparsec. Now, that's a funny unit, which you're probably not familiar with. Some of you will be, perhaps. But let me just tell you that 1 parsec is, so PC, that's about 3 times 10 to the 18 centimeters. So this is an enormously large length scale. Maybe that doesn't mean much to you, but let me also tell you that the distance from the sun to the galactic center is only 10 kiloparsec. Okay? Distance to the Virgo cluster, which is the closest kind of big thing near us, that's 20 megaparsec. Okay, so when we do cosmology, we're really going way beyond our local group, yeah, way beyond 100 megaparsec. The size of the visible universe is about 10 gigaparsec. Okay, so all cosmology that we talk about is between 100 megaparsec to 10 gigaparsec, essentially. Now, are these principles actually meaningful? I would say they are. This here is a picture that's from the 2-mass redshift survey. It's a bit old, but what it shows here is the local galaxy distribution. So every dot here that you can see color-coded as a galaxy. Okay, and the color coding indicates the redshift that the galaxy is at. And if you squint your eyes a little bit, it looks pretty smooth. Okay, there's this big gap here in the middle that's black. That's nothing, that's just the galactic plane because we can't see anything behind the galactic plane. So that's why they just cut it all out as black. But if you just ignore that black strip over there, squint your eyes a little bit, it's pretty homogeneous and isotropic. There's also, of course, evidence for homogeneity and isotropy coming from the cosmic microwave background, which is basically this old relic photon background that came from 400,000 years after the Big Bang. And they first detected that back in 65, where they saw this essentially homogeneous background of a temperature of about 2.73 degrees. Okay, that was back in 65 when Penzias and Wilson detected this homogeneous background. And of course, since then, we have had more observations of this background that also show some fluctuations in the temperature of this background of order 10 to the minus 5. Okay, so that was Kobe was the first one to detect these fluctuations back in 1992. And since then, we've also had WMAP, which was measuring in the 2000s. They had better resolution. And of course, we also have the Planck satellite, which is the most up-to-date measurement of this sort of fluctuations in the CMB background. Okay, so comparing the 3 generations, this is a picture that gets shown all the time. But you can see here that you have essentially something that's homogeneous and isotropic if you squint your eyes a bit. But there are also fluctuations that are of order 10 and minus 5. Now, if we stick with the idea of homogeneity and isotropy, and you try to describe this in the mathematical terms, then we appeal to what it means is that if we appeal to GR, what it means is that you can write down a metric that has 3 maximally symmetric 3 spaces. Okay, so you have 3 translational and 3 rotational symmetries in your space. Okay, so in other words, if you write down your metric, it will probably look something like this. So ds squared here is what you call line element, and then you have the time part. I use the minus plus 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 notation convention. And then here's the space part here, which I have written in spherical coordinates. And you can see here that you have one term called A, and A here is called a scale factor, and it's a function of time. And if you look at the rest of this expression here, you see here that there is this in the denominator K, okay? And this K quantity essentially describes the spatial geometry. Okay, so you could be in a hyperbolic space, in which case K will be minus 1. If we're in a flat space, then K will be 0. Anything that's positively curved would have a K of plus 1. Okay, in that case, your geometry is spherical. Now, what's so special about this? Okay, that's just curvature of your space. But the special thing here about this FLRW metric is this scale factor as a function of time, as I mentioned. And the idea of this scale factor is that if you take the scale factor at one time t2 and you divide it by the scale factor at another time t1, then this ratio here gives you the factor by which the physical length of something has increased between these 2 times. Okay, so that's, you have a length like that, and expansion of space would make that length actually longer. Okay, and that increase is given by this ratio. Okay. Now, so what it means is that, so here's the FLRW metric again, and there are these coordinates, right? T, R, and theta, and phi, etc. If you put an observer on these coordinate points and make them stay there forever, so they're at rest with those coordinate points, that observer is special. That observer is called co-moving observer. Okay? So you have here in this cartoon here, you have 4 co-moving observers who are sitting there very happy, and then space expands, and these four co-moving observers get further and further away from each other as a result of the expansion. Okay, so this is a forward in time. Okay, and the scale factor is also increasing. And yeah, so the coordinate distance between the co-moving observers, that doesn't change because they are at rest with the coordinate system, but they are moving apart from each other because physical distances change as a result of spatial expansion. Now, next concept I want to just remind you of is that of a geodesic. Okay, what is a geodesic? If you have no forces acting on your system, okay, so no external force like I don't know, electromagnetism or whatever, then a test particle moving on a geodesics of some space-time geometry, okay, that would be the shortest distance essentially on that space-time. Okay, so these are like geodesics are like straight lines in a curved space-time, if you like. So just to give you an analogy, everyone's flown, of, long distance, probably long distances on Earth, and if you look at flight paths, the paths they follow are essentially like geodesics. Okay, I mean, of course, there are small corrections because of weather, politics, whatever, but by and large, the flight paths followed by followed by planes are geodesics. Okay, these are the shortest distances on the surface of the Earth. Now, what's so cool about geodesics? Well, as it happens, if you have a test particle that is moving on a geodesic of that space of a space-time, then the space-time being ever RW universe in our case, then those particles will suffer cosmological redshift of its momentum. In other words, if I put a bunch of co-moving observers here on the coordinate points, okay, of my ever RW space-time, and you have a particle that is flying, like so, moving on a geodesic, then observer 1 here would measure some momentum, but by the time the particle gets to observer 2 would measure a different momentum, which is given by this expression. So P would go like a to the minus 1. Okay, that's cosmological redshift. In other words, the momentum of a particle decreases with expanding space. Okay, so keep going forward in time, and then the momentum goes smaller and smaller and smaller. Now, that's a nicer way to understand this, I think. You can imagine instead of momentum, you can think about, you can appeal to quantum mechanics. Okay, so the Broglie wavelength of a particle is 1 divided by the momentum, right? So you think about your space-time over here, you draw a wavelength, and you're stretching out your space-time. Okay, so the wavelength actually becomes longer. Okay, so that's exactly what's happening when we have cosmological redshift. Okay, so again, you can look at the wavelength as measured by some co-moving observer divided by the wavelength of a particle that is emitted at an earlier time by another co-moving observer. And this ratio here is given by the ratios of the scale factors at the two different times, the times of emission and the time of observation. Now, in astronomy in particular, this ratio tends to, it's common to have this ratio expressed in terms of this redshift parameter set. And essentially, so you have, the scale factor at the time of observation, which is usually today, divided by the scale factor at the time your photon or whatever was emitted, okay, TE. And this ratio here is parameterized by 1 plus Z, where Z is called the redshift parameter. Okay? So in other words, if you have a particle that was emitted at a very early time corresponds to a very small scale factor, A, but the redshift would be large. Okay, so you have therefore this kind of 3 sets of scales here. Redshift increases in this direction, time increases in this direction, scale factor increases in this direction, and there's a 1-to-1 correspondence between these 3 things. Okay, so for the rest of the lecture today, as well as tomorrow and on Thursday, I'll kind of be using these 3 things interchangeably as a measure of time. Okay, yeah, redshift, scale factor, T. I mean, I just sort of go between the 3 without thinking. I hope that's not confusing for you. Now, so that was the space-time geometry of FLW. To describe the stuff that is in the universe, in this sort of universe, we need to supply further information, and that comes in the form of the stress energy tensor. Okay, T mu nu looks like this. It's a 4x4 matrix and symmetric, and basically the different entries here correspond to different physical quantities. Okay, so you have pressure in the diagonal in the space part, energy density is here in the time part, time part. You have energy fluxes that are here, which you can also call momentum density if you like. And the off-diagonal entries here in the space part are called the shear stresses. We'll come back to these things later on, but just to remind you that the stress energy tensor usually looks like this. Now, because we're working with an FRW universe where the cosmological principle applies, okay, in other words, homogeneity and isotropy applies, then it turns out that there's only one viable form for the stress energy tensor, and it looks like this. Okay, it has to be diagonal because of homogeneity and isotropy. Yeah, you cannot have off-diagonal terms, otherwise you'll violate these two things. Okay, and so therefore we're left with just the energy density, which is up here in the time part, and the pressure term occupying the diagonal in the space part of the stress energy tensor. Okay, and I put a subscript alpha here to denote the fact that you can have different kinds of stuff in the universe, and different sorts of stuff would have different pressure and different energy densities. Okay. Now, furthermore, you see here that rho and p, they're only dependent on time. They don't depend on the spatial coordinates. And again, that follows from the fact that we want to describe a universe that is homogeneous and isotropic. So nothing can have a dependence on the spatial coordinates. Okay. Now, next question then is, how do these things evolve with time? Well, to figure out how these things evolve with time, what we have to appeal to is the continuity equation. Okay, and it looks something like this. And if you want to relate it back to concepts in relativity, essentially what we're doing is that we're applying the local conservation of energy and momentum. Okay, so that's the continuity equation. It's an equation of motion for the energy density rho. Okay, and as you can see, it depends on the rate of change of the scale factor, and it also depends on the pressure over here. Okay, and if you have one kind of stuff in the universe, you write down one continuity equation. And if you have 10 kinds of stuff in the universe, then you write down 10 of them, one for each substance that you have. Now, it's only one equation, as you can see, the equation of motion only for rho. You can ask, can I write down an equation of motion also for the pressure? Well, you can, yeah? Yeah, at this stage, yeah. But you could have them interacting with each other, in which case you just write down something to describe how energy is transferred between the two substances. Yeah, okay. So at this stage, there's only one equation of motion for rho. Okay, there's no equation for p. You can ask, can I write down an equation for p as well? The answer is yes, you can, but it will not be linearly independent. Okay, so it's useless. Okay, it's not an independent equation. And in fact, what you need to do is to supply a relation between rho and p. Because the relation between rho and p, so the relation between the energy density and the pressure, is a property of the substance you're trying to describe. It has nothing to do with cosmology per se. It's the stuff itself. It's a property of the stuff. Okay? And this relation is normally called the equation of state, sort of like the ideal gas law, if you like. Okay, that's an equation of state. Okay? And in cosmological applications, it's common to use a parameter called the equation of state parameter, and it's labeled W. And W is simply the ratio between P and rho, so pressure divided by the energy density. Okay, so that's equation of state parameter. Now, in general, W can be a function of time. But let's say, for argument's sake, that it's constant. Okay, then what you can do then is to put in P is equal to W times rho. Stick it into. Stopped working. Doesn't matter. You can stick it into this equation and solve it. All right. And when you solve that, there's a very simple expression you can write down for rho and how rho evolves with the scale factor. Okay, so it goes like rho. It's proportional to a raised to the minus 3, 1 plus the equational state. So this tells you immediately that depending on what kind of stuff you can have, or you have in the universe, this energy density would evolve differently with the scale factor. Okay, here's a list of some common stuff that we can just try to describe. I mean, like reasonable stuff that we can expect to find in the universe. So clearly, we have non-relativistic matter. We are non-relativistic matter. Okay, so atoms, in other words, or constituents of atoms, or bound states of atoms. And dark matter is something that we talk a lot about these days. It's the kind of stuff that doesn't emit light but feels gravity. The GR people like to call it dust. And thanks. Now, so this is all non-relativistic stuff. If you have non-relativistic stuff, what it means is that the energy of this stuff is dominated by its rest mass. It doesn't have much kinetic energy. And if it doesn't have much kinetic energy, it also means that it doesn't have much pressure. So it's conventional to set the pressure to 0, in which case the equational state parameter would be approximated by 0. Okay? So if I stick 0 into my solution here, what I immediately find is that the energy density in non-relativistic matter should go like a to the minus 3, which makes a lot of sense, because if I just have stuff sitting here and it's not being destroyed, not being created, and the only thing that happens is that space expands, then clearly the energy density has to go down with the volume. And therefore, we have this a to the minus 3 dependence. Remember that a is describing how length changes, right? So your volume is length cubed. Now, after that, we could also think about ultra-relativistic stuff, which is normally called radiation in GR speak. And we have a lot of radiation around. We have a lot of photons. We've seen the CMB, that's photons, entirely photons. We have other backgrounds as well, but we're photons. We have relic neutrinos, that's why we're here talking about neutrinos, right? We have relic neutrinos. And at least at very early times, after these neutrinos were produced, they were quite fast, traveling at the speed of light. And we probably also have gravitational waves, maybe from inflation. We don't know, we haven't seen them yet, but it's possible they're there. These things are all traveling at, all moving at the speed of light, which means that the equational state parameter is 1/3. This is something that comes from thermodynamics. Okay, and again, if I'm to stick this WR is equal to 1/3 into my solution, I will find that the energy density of radiation rho r goes like a to the minus 4. So you have an additional factor of a to the minus 1 relative to the matter case. But in the end, that makes sense, because remember that there's a thing called redshifting. Okay, so if my energy density is, well, ultra-relativistic, then the energy is equal to the momentum. Okay, E is equal to P for ultra-relativistic particles. And momentum redshifts like a to the minus 1. And that's where that extra factor of a to the minus 1 comes from. You have redshifting, a to the minus 1, and then volume expansion, which gives you a to the minus 3. And last but not least, you could also have funny things around that are neither radiation nor matter. So the most famous thing that we could describe is that of maybe a vacuum energy, or sometimes called a cosmological constant. And in this case, this kind of stuff is, well, seriously weird, because the equational state parameter is -1. Okay, and essentially, kind of vacuum energy is corresponds to the kind of energy that is associated with your space. So the more space you have, the more energy you have. So you expand the space a lot, you end up with a lot of energy. Okay, and here the rho, when you have W is equal to -1, then sticking it into this expression, what you'll find is that the energy density in this kind of funny vacuum energy is a constant. Okay, so these are the three things that we talk about that make up the lambda CDM model. But there are other forms of energy densities that you could try to that have equational state parameters that differ from these three cases. Okay, so for example, massive neutrinos, for example, will start off like ultra-relativistic radiation, and then eventually they become non-relativistic matter. So you have this kind of transition from 1/3 for W to 0. Okay. Similarly, if you're interested in dynamical dark energy, then the equation of state parameter for dynamical dark energy component could also be different from -1. It could be maybe minus 0.9, or I don't know, you could even have phantom energy, in which case you have something that's even more negative than -1. Anyway, so we have these three things, and let's try to plot them. Okay, so what I have here is the log of the energy density versus the log of the scale factor. And the three lines here correspond to the three types of energy densities from the previous slide. So I have dark energy here, or lambda, rho lambda, which is a constant, goes like that. And we have the red line here, which corresponds to the energy density in radiation, which goes like 8 to the -4. And because it goes like 8 to the -4, we know immediately that at very early times, this form of energy density must dominate. Okay, so when A goes to 0, this blows up. And then in between, you have the energy density of matter, goes like 8 to the -3. So it doesn't blow up as fast as radiation as you go to A goes to 0. But as you take it to larger values of the scale factor, it will eventually dominate over the radiation, but then drop below the energy density due to lambda. Okay. So we have names for these different epochs where different types of energy density dominates. So over here, where the red line dominates, it's called radiation domination. Where the blue line dominates, you have matter domination. And where lambda dominates, you have lambda domination. And where the lines cross, where the red and the blue lines cross, this is matter radiation equality. That's because that's the point where the matter and the radiation energy densities are equal. And over here, we have matter lambda equality, which is basically analogously defined. And if I furthermore put in the cosmic pi that we know about, where you have 75 dark energy, 25% dark matter, etc., then what we have is basically these ticks over here. We live somewhere here today, and this point here corresponds to scale factor to -3, 8 equals 10 to -3, -6, -9, so on and so forth. And just to put in also the major events that we expect to have taken place in the early universe, we have structure formation, which takes place entirely during matter domination. The last scattering surface of the CMB is a little bit after matter radiation domination, matter radiation equality, and nuclear synthesis. It's a really, really early universe event taking place during radiation domination. Okay, and the fact that these lines here evolve differently with the scale factor also explains why it is that we have the composition of the universe looking like this today, and the composition of the universe looking kind of different at an earlier time, okay? Because the different forms of energy density evolve in different ways. Cool. Now, one more thing that I want to say here, and that's the Friedmann equation. It's actually very important that I talk about the Friedmann equation. Because so far we've talked about how the energy densities evolve according to the scale factor, but I haven't actually said anything about how the scale factor itself evolves with time. And that is described, this evolution of A is described by the Friedmann equation. Okay? Normally you see the Friedmann equation in this form, where you have the A dot here, so dA dt divided by A. This thing is called a Hubble parameter, H. Okay? H is equal to A dot divided by A. And if you square this thing, then this quantity here is equal to, is actually something that's proportional to the gravitational constant, okay, G. And then you have a sum here over all forms of energy density that you have in the universe, okay, rho A, all the different kinds of stuff that you have, radiation, matter, weird things, vacuum energy, whatever, they all go inside this sum, okay? And lastly, because there's a possibility that your space is curved, there's also the curvature term, which is entering into the equation here. So minus k divided by a squared. And k, as said before, could be 0 for a flat universe, or plus or minus 1 if you have something that is curved. If you wonder where this came from, this Friedmann equation, essentially it is this Freeman equation is itself derived from the Einstein field equation. So basically, you stick your metric into your Ricci scalar and your Ricci tensor, and then you equate that with the stress energy tensor that we wrote down in the previous slide. Yeah. I think Freeman actually came up with this first. And then they all worked at different times. And maybe I don't really know historically what happened, but I think Freeman actually came up with this first. But the thing is that there were these four, Freeman and Lemaitre, all working in the 20s or so. And Robertson Walker are really much later, as I understand. Yeah. Yeah, I don't know. I don't know. I don't know, really know. I mean, if you read Cope and Turner, for example, Cope and Turner says Robertson Walker, but that's American. They are American, so of course they only care about Americans. Um, and then you have FRW as well. And I think L only kind of made an appearance more recently when the Belgians were kind of indignant about their contributions not being recognized. Yeah, I said FRW for a long time, but then I had a postdoc who was Dutch, and he felt like he needed to defend the Belgians. So I started saying FRW because he insisted. Yeah, yeah, yeah. Right. Okay. So that's the Freeman equation, which could have been FRW equation. I don't know. Anyway, uh, you probably have also seen the Freeman equation in this form. Okay. And essentially, what I've done here is to turn this previous equation here, and then defined the energy densities in terms of these reduced energy density parameters, which are normally called omega. So what you do is that you divide them through by a critical density. Okay, the critical density is defined as the Hubble parameter at that time divided by 8 pi g times 3. And once you do that, the Freeman equation in the previous slide can be massaged into this form. Okay, so that's the matter density goes to 8 to the minus 3. The radiation part goes to 8 to the minus 4. That's the cosmological constant, or vacuum energy if you like. And I've also turned the curvature term into something that looks like a reduced energy density parameter. And it's basically just the curvature parameter k, and then you divide it through by the Hubble parameter square. All right? Yeah. It's a property of the space-time. Yeah, it's this. Yeah, it's a property of whatever space that you live in. So it's a constant. Yeah. No, no. You're either curved, or positively curved, or you're flat, or you're negatively curved. The omega k parameter itself, however, can be dependent on. I mean, this term here can be dependent on time. Yeah. So curvature may not matter if you have a huge amount of energy densities in different forms, then the curvature term could end up being not really apparent in your observations. Yeah. Which is probably the case today, for example, because the next thing I'm going to say is that at the moment, the curvature that we measure is tiny. Okay, which doesn't mean that there's no curvature. It's just that we don't really see it, so we pretend it's not there. Okay. Yeah, so flat universe means that the curvature parameter is 0, as said. And if you look at the current observations at the moment, omega m is about 0.3, omega lambda about 0.7, and the curvature parameter is constrained to be much less than 0.01. Okay? That picture we don't need to see. And last but not least, just to highlight this, you may also have seen the Freeman equation in this form, where instead of writing the scale factor as 8 dot, okay, you write the acceleration of the scale factor, so you have a double dot divided by a. And writing the Freeman equation in this form has the advantage that it shows you immediately whether your expansion is accelerating or decelerating. Okay, so acceleration corresponds to the case when this stuff here in the sum is less than 0. Okay, because if it's less than 0, it's negative. You have negative multiplied by minus sign, you get something that's overall positive on the right-hand side. So that tells you have an accelerating expansion. Okay, and if I play around with this expression, I can turn it into a requirement on the effective equation of state parameter for acceleration to happen. And what you find is that the W effective has to be less than minus 1/3 in order for the acceleration, for the expansion to be accelerating. And similarly, you have deceleration, if the sum here evaluates into something positive, and that corresponds to the case where W effective is larger than minus a third. Okay, so that's my cosmology 101, and hope that was not too repetitive for those of you who already know this. And now what I'm going to do in the next half or so is to talk about the hot universe. Okay, ready? Let's go. Okay, so we're moving to this part of our timeline. And so obviously now we're going back in time, okay, to the early universe. And the early universe was a very hot and dense place, okay? And we know that because you dial the clock back and everything got denser, and there's also cosmological redshift, right? So if you go backwards in time, then you're basically blue shifting everything. So everything was hotter and denser at early times, in other words. Now, if you pack a lot of particles together in a very dense and hot place, and they're very energetic, then what happens is that these particles will start to interact. They will start scattering off each other, and maybe they will form bound states. All sorts of things can happen. Now, we don't really know exactly what kind of interactions there are, because that depends on the particle physics theory. But we do have the standard model of particle physics, so at least we can work with that. Okay. Now, no matter what particle physics theory you're dealing with, there's one concept that is very important in the whole discussion of hot universe, early universe physics. And that is this relation over here. Gamma is called the interaction rate per particle, and H here is the Hubble expansion rate, which is the same Hubble expansion that we saw earlier. And if it is the case that an interaction rate for particle per particle exceeds the Hubble expansion rate, so in other words, it's much larger, then that interaction can be taken to be in a state of equilibrium. Okay, this is like the one thing that people talk about when we consider particle physics processes in the early universe. Is the interaction rate larger than Hubble or not? Okay, the first thing you think about. Now, here's a classic example, and that is the weak interaction, which is actually very good for us because that's also the most relevant example for neutrinos. So, what do we have? Say you have a gas of ultra-relativistic particles with a temperature of T. Then what we can do is to estimate this weak interaction rate per particle. Okay, so gamma, int, and obviously it has to depend on the cross-section over here. So the cross-section is sigma, and for weak interaction, you can put in the Fermi constant square, and just to make sure that you have the right dimensions, you can put in T square here, because that's the only energy scale we have, if it's ultra-relativistic. We need to multiply that by the relative velocity, but since this is a really ultra-relativistic gas, so everything is moving at the speed of light, in that case, the relative velocity is also speed of light. So in these units, v is equal to 1, roughly 1. We have to multiply that by the number density of scattering centers. So you have particles that are scattering all over the place, right? And I need to know how many things are scattering off. And that's the n that is appearing here. And number of scattering centers would go like temperature cubed, just from dimensional grounds, on dimensional grounds. And so if you combine all of these things together, what you'll find is that the interaction rate goes roughly like the Fermi constant square times the temperature to the power 5. Okay, so that's my interaction rate per particle, per neutrino, if you like. Now, the next thing we need to consider is the Hubble expansion rate, right? And we saw earlier that the Hubble expansion rate is essentially given by the sum of all the energy densities that you have in the universe. There's also a dependence on the curvature, but as I also demonstrated earlier, the curvature parameter is small in any case. And if you go to the early universe and everything was seriously dense, the curvature parameter doesn't really matter. Okay? So we just have this stuff over here, and again, if I have ultra-relativistic stuff, the energy density on dimensional grounds would be given by temperature raised to the power 4. So in the end, what I have, when I try to evaluate what is the temperature dependence of the Hubble rate, I'll get T squared divided by the Planck mass. Okay? For those of you not familiar with the Planck mass, if you square the Planck, that's basically just the inverse of the of the gravitational constant square root. Okay. Now, so I have this expression and this expression. I know what they are. I know what GF is. Okay. I also know what the Planck mass is. Things you can look up on Wikipedia if you like. And so if I form the ratio between gamma int and the Hubble expansion rate, what I'll find is something like this. And I plug numbers in. This goes roughly like T to the T cube, 1 MeV. Okay? So what this means immediately is that if I want the weak interactions to be in a state of equilibrium, then this ratio must be much, much, much larger than 1. Okay? To make this ratio much larger than 1, yeah, I need T cubed to be much larger than 1 as well. So if I just use this expression, what I'll find immediately is that if the temperatures are much, much, much above 1 MeV, then even the weak interactions will be in a state of equilibrium. Okay? If I go below, the weak interactions will not be in equilibrium, but if I go above this temperature, even that will be in equilibrium, which is quite amazing because you don't get it anywhere else, not in the sun. Maybe in a supernova, but definitely not in ordinary situations. And if I go back to this picture over here and ask where is that situation attained, it's basically all the way here at a very, very high redshift. Okay, so you have structure formation, large carrying surface, big bang nucleosynthesis. If you go even earlier, even the weak interactions will be in a state of equilibrium. Now, so what? Well, if you are if an interaction is in a state of equilibrium, what it means is that all the particles that participate in that interaction will have a phase space distribution that is described by one of the equilibrium forms. So if you have a fermion, that equilibrium form would be the Fermi-Dirac distribution, which would be this thing over here, but with a plus sign. If the particle that is participating in this interaction in equilibrium is a boson, then you'll pick the minus sign because that would correspond to the Bose-Einstein distribution. Okay, so this is the equilibrium phase space distribution. T is the temperature, and all the particles that are participating in interaction in equilibrium will have the same temperature. Okay, that's one of the definitions of equilibrium. That's zeroth law of thermodynamics. Additionally, the chemical potentials will also satisfy the relation that you sum all the initial chemical potentials that will be equal to the final state chemical potentials. Okay, so that's mu. Now, I wouldn't be talking much about chemical potentials because in standard cosmology, the chemical potential is essentially related to any kind of asymmetry that you have in matter and antimatter. And we know that the matter-antimatter asymmetry is tiny. We're talking about 10 to the minus 10. Okay, so in the standard case, these mu parameters tend to be very close to 0. So I'm just going to call it 0 without complicating our lives. Okay, so that's the last word you'll hear about chemical potentials here. But I will, however, add that there are situations it is possible in non-standard cosmologies to generate a mu that is not 10 to the minus 10, but significantly larger. Now, so if you have 10 to the minus 2, you're probably still okay. Larger than that, you'll be in trouble. You'll also be in trouble with the CMB. But even 10 to the minus 5 would be considered very large. But you need 10 to the minus 5 if you want KV sterile neutrino dark matter. Yeah, for it to get around the bounds and yeah. So I mean, it wouldn't be observable because it's still very small from the observational perspective. But it would be considered large from relative to the matter-antimatter asymmetry. So people sort of don't really like these large asymmetry scenarios. Yeah.
Big Bang is Gamma, who was student of Friedman. So he was not interested in cosmology.
Yeah.
He eventually changed his mind after studying nuclear physics, and then this is a student of Friedman who created this
Oh, yeah. BBN. Yeah, that's right. Yeah, BBN.
Interesting, let's say, sentence.
Yeah, that's right. Yeah, indeed. Yeah, that's gamma and alpha and beta and these people. Yeah, indeed. Yep. Okay, so that's the equilibrium thermodynamics. Now, um, I've written this down. Normally, we don't really, I mean, sometimes you care about a precise distribution, but most of the time, we're more interested in the bulk quantities like number density, energy density, and pressure, because it's the energy density that goes into the expansion rate. Okay? So if I am given a phase space distribution F, then I can, to find the energy density or number density or pressure, all I have to do is essentially just to integrate these functions in momentum. Okay, so the number density would be a simple integration of F. Energy density, you have to weigh it by the energy per particle at each P. And then pressure will be given by this expression. Don't worry about the precise definitions. Um, But just examine, just look at the box here where I've boxed in the energy density. Okay. Now, if you want to have a general expression for the energy density, this is what you write down. And normally, for the distribution functions like Fermi-Dirac or Bose-Einstein, this is not analytically soluble. Okay, it's only solvable in the ultra-relativistic limit, in which case what you'll find is a dependence on rho that goes like the temperature to the power 4. Okay, that you can plug into Mathematica and do very easily. And that is the solution if your particle has a rest mass that is much less than the temperature. Okay. Another analytical solution you can get is in the non-relativistic limit, and that's the case when the rest mass of the particle is larger, much larger than the temperature of of the bath. Okay, in that case, what you find is something like this. Don't worry about the prefactors. The main thing here is the fact that you have this exponential raised to the minus m divided by t, and I've told you already that m is much larger than t. So what this means immediately is that this exponential factor is tiny. Okay, that's called Boltzmann suppression. Okay, so in other words, the energy density in something that is in equilibrium and is non-relativistic is highly suppressed relative to the energy density in the relativistic particle. Okay, so what this means is that if I go back now to look at my Hubble expansion rate, which is over here, and I try to add up all the stuff that I have in the universe in this sum, in the energy densities, of the energy densities, this sum here will be completely dominated by relativistic stuff. Okay, the non-relativistic stuff, they just get so suppressed, you won't even see them. Okay? So, it will be dominated by relativistic stuff, and it's common to parameterize this sum in terms of a G star parameter. Okay, so what we have done here essentially is to factor out this T gamma fourth, that's the photon temperature, because that's roughly how we expect relativistic stuff to behave like, the energy density to behave like. It goes like temperature to the fourth, right? So we factor that out, and whatever that remains, temperature dependence that remains, will be here in the G star parameter. Okay, and what G star of T and how that depends on T and what is the number is specific to the particle physics theory that you have in mind. So this picture here shows the G star of the Standard Model. Okay, so plotting here is G star, that's the black line, and that's the temperature. So temperature goes this way, and time goes forward this way. Okay, so hot here, cooler over here. And if you follow the black line over here, it's interesting. You start off pretty large, or over 100, and that is because if you are at these extremely high temperatures, then every particle species that you have in the Standard Model would be ultra-relativistic. Okay, so you have this huge G star up here, and then the line it starts to decrease, and because as the universe cools, some of the rest masses of the particles will become larger than the temperature. So you see here, for example, the top. Yeah, the top mass is large. Okay, and they go the top quark goes non-relativistic. They drop out of the contribution to G star, and so on and so forth. You go here, bottom, W, Z, Z naught, H, Higgs, they're all dropping out here. And then you have this very, very sharp drop over here, which corresponds to the QCD phase transition. okay, or quark-hadron phase transition, if you like. And what happens there is that initially you start off with all the quarks and the gluons forming a quark-gluon plasma. So you have all these ultra-relativistic degrees of freedom in quarks and gluons floating around at these high temperatures. And suddenly you hit the QCD phase transition when everything becomes confined. Okay, so all your quarks become bound into bound states and nucleons or mesons and various things. And these things are heavy and non-relativistic. Okay, so that's why you have a sudden drop, because they suddenly become confined. You suddenly lose all the relativistic degrees of freedom. G star drops down. Okay, and we keep following this line here. Even the pions at 130 MeV, they become non-relativistic, and weak interaction goes of equilibrium roughly around temperature of 1 MeV. Okay, from 2 slides ago, and nucleosynthesis starts roughly here. Okay, and for us doing neutrino physics, the most interesting part is here. And that's basically the point at which the weak interaction goes out of equilibrium and where the neutrino background forms. Okay, just to remind you again what's happening, here's the formation of a neutrino background, a schematic for the formation of a neutrino background. And what you have here is that, initially at high temperatures, you have the neutrinos that are kind of just doing a random walk around a thick soup of electrons and positrons. And because of the frequent scattering, you are maintaining the neutrinos in a state of equilibrium, and they follow a Fermi-Dirac distribution. But as the universe cools and the weak interaction goes out of equilibrium, then the neutrinos will stop interacting effectively with the electrons and the positrons. So what happens at temperatures below 1 MeV is that the neutrinos will start to free stream to infinity. Okay, and that's what gives rise to this neutrino background, which is over here somewhere. Okay, just before nucleosynthesis. Yeah. Yeah. This one. The dash and the. I'll get that. I'll get to that in a bit. Okay, it's coming up actually. Okay. Right. I'll get to that in two slides actually. So now, so that's the cosmic neutrino background. Let's look at this in a bit more detail at what's happening. So what we want to focus on is the temperature range between 10 MeV and 0.1 MeV. Okay, so going back here to this plot, we're looking at about here to there, okay, where this curve drops down. Okay, right. Now, let's ask what kind of stuff we have in the universe at that time. So at 10 MeV, the only things you have left are the neutrinos, and there's 3 families of them. And they're still very, very relativistic because we know that neutrino masses are very small, so probably less than 1 electron volt. So they are very relativistic, all good. We also have the QED plasma. The QED plasma consisting of photons and E plus E minus. And at these temperatures, photons are always ultra-relativistic, of course, and E plus E minus would be ultra-relativistic at 10 MeV for sure. Now, within the QED plasma, you always have electromagnetic interactions, and they're always in equilibrium in this time range, in this temperature range, because electromagnetism is just it's one of the stronger interactions, if you like. Okay, at least in the context of cosmology. And so you have all sorts of scattering processes, annihilation that could happen in the QED plasma. Now, the neutrinos are interacting as well if you are at a temperature larger than 1 MeV, because that's when the weak interactions are in equilibrium. And so you could have neutrinos scattering off each other, new bar going to new bar. And these 2 sectors also talk to each other because the neutrinos can scatter on E plus and E minus. So the 2 sectors are talking as well. Okay, so this sector talking within itself, neutrinos talking amongst themselves, and then the 2 sectors talk to each other as well. But if I let the universe cool a bit and I go to a temperature significantly below 1 MeV, then I'll still have the QED interactions because they are quite strong in this context. But the neutrinos won't talk amongst themselves anymore because the weak interactions have gone out of equilibrium. I mean, even if they talk, they can talk amongst themselves, but it won't be very efficient. Okay, and the cross-sector talks between QED and the neutrino sectors would also not be effective. So you also won't have these interactions occurring at a very large rate. So given this information, what I can do now is to try to plot the thermal history of neutrinos. Okay, so I'm plotting the events that happen. Here's a timeline, time moving forward like this, so temperature goes this way. And I'll tell you the neutrino temperature as well as the phase space distribution. So to begin with, I have, at high temperatures, the neutrinos coupled to the QED plasma, where the weak directions are holding the neutrinos' weak interactions in equilibrium in relative to expansion rate. Okay. Now, because the neutrinos and the electrons are talking to each other, this also means that the neutrino temperature and the photon temperature would be the same. Okay, because when things are in equilibrium, the temperature of the interacting particles must be the same. Okay, so T nu is equal to T gamma. And as we saw earlier, the phase space distribution is essentially that of a relativistic Fermi-Dirac distribution. Then I let the universe cool, and at some point I get to 1 MeV, and 1 MeV is special because that's when the weak interactions drop out of equilibrium, and the neutrinos decouple from the QED plasma. So we call that event neutrino decoupling. And that's roughly defined by the temperature at which gamma int is roughly equal to the Hubble expansion rate. Okay? Now, if I consider the temperature of the neutrinos, it will still be the same as the photon temperature, because nothing else is, okay, they stop interacting, but it's not like anything else is happening. So they just keep moving forward and as if nothing has happened. Okay? And the neutrinos will also retain their relativistic Fermi-Dirac distribution. But something else kicks in if I go down to a lower temperature. Namely, if I go down to a temperature that is roughly equal to 0.5 MeV. What's 0.5 MeV? Well, that's essentially the electron mass. Okay? So when you get to this point, when the temperature is roughly equal to the electron mass or below, then an interesting thing happens. Okay? Well, you have E plus E minus annihilation happening. Now, normally, is E plus E minus going to gamma gamma, and gamma gamma going to E plus E minus should be occurring in both ways if you're at a high enough temperature. Okay, in other words, if you have, you can have your E plus E minus annihilating into photons, and if the photons are energetic enough, you can have the backward process as well. But the thing is that if your temperature is less than the electron mass, and the photons are not sufficiently energetic for this first process to proceed. Okay, so you can have E plus E minus annihilation going to gamma gamma, but not the other way around because it's kinematically forbidden. Okay, so in other words, what you're doing here at temperature of 0.5 MeV is that you're suddenly converting all of the energy that is initially in the E plus E minus into gamma, into photons. And there's a name for that. It's called reheating. Okay, you're heating up the photons, or maybe not reheating, but just heating of the photon bath. Okay? Now, this is interesting because this annihilation event will only heat up the photons, but not the neutrinos, because the neutrinos have already decoupled. They're not even talking to the photons, so they wouldn't even know that this heating has taken place. Okay? And the end result of that is that the neutrinos will come out of this reheating event a little bit cooler than the photons. And that relation between the neutrino temperature and the photon temperature goes like this. Okay? I'll say to you in a bit how I calculate that, but let me just point out to you that this sudden drop here in the G star essentially corresponds to the fact that you are losing all the electrons and positrons into photons. Okay? Now, as for why you have a dash curve versus a solid curve, that is because this is the energy density G star. I can also define one for the entropy. And that's because of a slightly different definition, you have two different curves. Okay. Now, okay, so why do I have this really funny expression over here? Well, and how do I get that relation? To get this relation out, what I need to appeal to is conservation of co-moving entropy. And essentially, the idea is that if you have a system that is in a quasi-static kind of equilibrium, okay, in a quasi-static way, so you letting the universe expand, but then expanding kind of slowly enough that you don't really disturb the equilibrium. That's what is meant by quasi-static. Then the co-moving entropy density, capital S, is approximately conserved. Okay? And the co-moving entropy density is defined in this manner. So you add up the energy density of each particle species with the pressure divided through by its temperature, and you sum it off. That's the co-moving entropy density. And this thing here, okay, S would basically correspond to the entropy in this box defined by the 4 co-moving observers, and it's the same, yeah, even with the expansion of space. So, how do I use this to get the neutrino temperature out? Well, that's quite straightforward, a calculation. And essentially the way you would do it is to look at what happens in each sector. So you look at what happens in the QED sector and what happens in the neutrino sector, and then you consider what happens before annihilation, the entropy that is contained there in the QED plasma before annihilation, which would be this, and the entropy density, co-moving entropy density contained in the neutrino sector before annihilation, which will be given by this expression. Okay? And you can do the same thing also with the entropy density contained in the QED sector after annihilation. And so as opposed to 11, you get a 4, because after annihilation, you don't have any E plus E minus, you only have gamma. So it's just, you have a drop in the number of relativistic stuff. And similarly, for the neutrinos, you have the entropy density here. Okay? And it's the same as before because the annihilation does not affect the neutrinos. Okay? So these are the 4 things I can write down. And then the next thing I need to do is to essentially just demand that I have entropy conservation in the neutrino sector, okay, so that the entropy contained in the neutrino sector before annihilation is the same as that after annihilation. So that's this relation. And when I equate these 2 expressions together, what I find immediately is the relation between the neutrino temperature before and after annihilation. Okay? I can do the same thing also with the QED sector. I equate the entropy density in the QED sector before annihilation and after annihilation, so that's that. And I equate these 2 things together, I immediately pick up this 11 divided by 4 factor raised to 1/3. One more thing I need to do, I have to relate the pre-annihilation photon temperature to the pre-annihilation neutrino temperature, but I know what that is. They have to be the same because before annihilation, before annihilation at some time before decoupling, immediately after decoupling and before annihilation, the neutrino and the photon temperatures are the same. So I can do that. And with a little bit more algebra, I can eventually massage it into this form. Okay, so the 4, 11 is really because of the degrees of freedom that are relativistic degrees of freedom that are there in the QED plasma. So where that comes from. Just a couple more slides and I'm almost done. Now, so that's the C nu B, and it's sitting there. And if you keep, it will just be sitting there for after its production. And if we look at temperatures much less than 1 MeV, at 1 MeV, as I said earlier, the phase-space distribution will be described by this relativistic Fermi-Dirac distribution. Okay, and the temperature, as we've seen, would be related to the photon temperature in this manner. So if I look at look at the background today, what I'll find is that in this neutrino background, we have a temperature of 1.95 Kelvin, because I know the photon background is 2.73 Kelvin, right? So I just use this relation to figure out what the present-day neutrino temperature must be. Now, what about the phase-space distribution? What happens to that? Well, clearly, after decoupling, the C nu B is just free streaming. It's not doing anything. It's not scattering. Okay? So the only thing that can happen after decoupling is that the temperature will redshift, like a to the minus 1, and the momentum of the neutrinos will also redshift, like a to the minus 1. So if P is redshifting like a to the minus 1, and T is also redshifting like a to the minus 1, then nothing happens in this exponential. Okay? So what this tells me immediately is that the phase-space distribution of the neutrinos would remain the same relativistic Fermi-Dirac form even now, even after the neutrinos become non-relativistic. Okay, this is probably a little bit weird, but it's really just a consequence of Liouville's theorem, if you want to appeal to classical mechanics. I'm not destroying neutrinos, I'm not creating neutrinos after decoupling. So the co-moving number density of the neutrinos must remain the same. Okay, and if I calculate this, it's 100. Calculate the co-moving energy number density of neutrinos, I should find about 100 neutrinos per cubic centimeter per family of neutrinos and antineutrinos. So the number density is easy. Energy density is a little bit trickier, and that is because it depends on kinematics. Recall that from like slide 5 or something, I talked about how the energy densities in different things evolve like. And if you have an ultra-relativistic stuff, the energy density goes like 8⁻⁴. And if the stuff is non-relativistic, it goes like 8⁻�3. Okay? And so for neutrinos, you expect a transition from this 8⁻⁴ behavior to the 8⁻3 behavior, which is actually best seen if you look at this picture. Okay, so if you just focus on one of the red lines, that's the energy density in a neutrino. Okay, a massive neutrino with a mass of 0.05 electron volt. And also plotted alongside that is the green line, which is the photon energy density. And as you can see here, the neutrino energy density more or less tracks the photon energy density at early times. But as you move forward in time and increase the scale factor, you start seeing the red line deviating from the green line. And that is because the neutrinos become non-relativistic. Okay? And in fact, if I look at the red line over here, it's parallel to the blue line. And the blue line is the energy density in the cold dark matter. So you start from a relativistic behavior, and eventually you end up with a non-relativistic behavior. You can also see that in this plot here, where I'm plotting the reduced energy density parameter. So where at every point here in time, I have normalized the energy density to the critical density at that time. And you see the same thing. So you have the red line tracking the photon green line up here. But then as you move forward in time, when the neutrinos become non-relativistic, the line here flattens out, whereas the green line keeps going down. Okay, and the red line here is tracking the blue line, which is the energy density in cold dark matter. Okay, you can also compute what the energy density must be. Okay, by at here, so you just take rho is equal to m times nu, which is what you would use if you have non-relativistic particles, and this relation here gives rise to this famous expression relating the reduced energy density parameter in neutrinos to the neutrino mass. Okay. And here's the summary, and I think that's the last slide, and I better stop here. Yep. Okay, thanks for your attention. Questions? Which one? This one? So if you here. So n is something I can calculate because n. So the phase space distribution is Fermi-Dirac, and to get the number density, I integrate the Fermi-Dirac distribution in momentum, and that's what gives me this 6 divided by 4 and zeta function pi square blah blah blah. Okay, I know the temperature of the neutrino background that is related to the temperature of the photon background. So I can just plug this in to give me this number. Okay? Now the next step is to realize that if my neutrinos are non-relativistic, then the energy density is simply the mass, rest mass of the particles multiplied by the number density. And so that gives me rho. The next thing I need to do is to compute the reduced energy density parameter by taking rho divided by the critical density. The critical density is just 3 h0 squared divided by, g. And so you have to change units a few times, but ultimately that's what you would get. Mass should be expressed in electron volt, I should say, explicitly. Yeah. Little h. Yeah, little h I didn't say. It's called the, I don't know what it's called, reduced Hubble parameter maybe. And Hubble parameter is, well, right, this right. Oh, don't pull that off. H. And what people do is to say this is 100, and then you define a small h, and then kilometers per second per megaparsec. Okay, so if h is 70 kilometers per second per megaparsec, then this corresponds to a small h or 0.7. It's just nicer to work with dimensionless things. That's all. Yeah. Ah, absolutely. H naught. H naught is the Hubble parameter today because it's an evolving quantity. Correct. Yeah. Yeah. It is pretty impossible, but that hasn't stopped people from thinking about how to do it. So that's an idea that's been floating around for since the 1960s, and the idea is that if you have something that's a beta decaying nucleus, so something that is like n going to n plus electron plus an antineutrino, okay, and that's basically the process that you use to do neutrino mass measurements in the lab, right? Tritium beta decay, okay. You look at the energy of the electron, okay, and you plot the endpoint power spectrum. So this is E, you'll get something like that. The Q value is the difference between the two, the mass difference between the two nuclei, and this thing here is essentially something that's proportional to neutrino mass. You've probably seen that one before. So if this process happens, then you could also have a capture process where you have nu E from the C nu B, n prime going to n plus E minus, okay? And if this process happens, so you have a decay nucleus, it captures a background neutrino, then what you'll find is something like this over here. But the number of events is tiny because these are, the background neutrinos are weakly interacting, they are not very energetic, and you have this huge uh, endpoint from the. That's right, yeah. That's right. 10, less than 10. Yeah. Yeah, the number that is floating around is the number of events is maybe, you said 8, right? I always remember it's less than 10. That's quite 8. 8 events, yeah? Yeah, 100 grams of tritium, yeah, H3 per year. And 100 grams of tritium is a lot. I think there are 0.1 milligram of tritium in Katrin, something like that. I actually did ask someone if there's, I asked Christian Weinheimer if there's 100 grams of tritium in the world, and he said yes. Huh? No, no. I didn't know where it was, but he said it's true. Right, yeah. 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 Weinberg, yeah. Goes back to the 1960s, and then, yeah. I th- That's a prototype. Yeah, yeah, yeah. But that's not really, I don't think that's a problem. I think that's a fundamental problem. Yeah, yeah. Now, this one? No, it's, well, I mean, this cosmological, evolution happens on cosmological time scale. So we can measure, oh, yeah, that's exactly the point. That's what I was going to say. The problem is not so much 100 grams. I think the problem is the fact that you have to be able to resolve this gap. And this gap is 2 neutrino times neutrino mass. So these two things are tied together: measuring neutrino mass in the lab and measuring neutrino background. If you don't measure neutrino mass in the lab, you're not going to see the neutrino background in this kind of experiment. Yeah, because this endpoint will swarm the tiny signal over here. Okay, energy resolution is hard with gaseous kind of tritium because they are flying, the gas particles are flying, molecules are flying around, which is what is done in Katrin. And Ptolemy, as I understand it, they're trying to embed the tritium in the lattice, in the graphene, or I've forgotten what funny thing. But even that has problems in itself because of the Heisenberg uncertainty principle. Yeah, yeah,
Because the neutrino, which is more important for this measurement, is electron neutrino. No? Today, Gabriela discussed that somehow electron neutrino is a mixed stage. However, precisely, this electron neutrino is mostly in E1, and E1 is the lighter. The lighter has the biggest problem with the resolution. The one which has the smallest mass is more prone to the kind of problem that we want to discuss.
yeah. So it's hard. That's the bottom line. Yeah, yeah. That's right. Yes, that's right. Cocoa and manganese. That's right. Yeah, yeah. I remember that. I remember that paper. Yeah, yeah. Yeah, Weinberg was doing asymmetry, I think. He was specifically looking about Pauli blocking. Yeah, was talking about Pauli blocking in particular, I think. Yeah.
So this is a very good point. So let me make a comment on this. Tomorrow, Gabriele will discuss about Majorana, the possibility that neutrino in the rest frame are same as antiparticle. Okay, this is a definition of what is the meaning of now. Indeed, if mass is zero, you do not distinguish. So somehow it's not true. So somehow, if this number 8 is correct, for neutrino are non relativistic. If neutrino become, say, non-relativistic, Majorana does not change. For Dirac changes continuously because of this point that you mentioned. So the more the mass become small, the more you mix the two cases Dirac and Majorana. It's interesting point, very interesting point.
There's a question on the back. You can try. You can do that. Yeah. So all the evidence we have of the CNUB at the moment come from cosmology, and one of the things that you can look for is so this parameter. So I showed over here this prediction, right? So that's the high energy, the early universe prediction when that applies when the temperature is larger than the neutrino mass. So this thing here essentially corresponds to. Let's see if I can get back to one of the first slides over here. So you see in this plot here, you have 10% neutrinos and 15% photons. This is actually a standard model prediction. So it usually goes under the name of N effective, okay? And you can calculate that very well if you want to. Take standard model physics and just churn away. That gives you a number, and that's basically the ratio between the neutrinos and photon energy density. And with that, you can actually test it in, say, CMB anisotropies. Because if you change the ratio here, the CMB sky will look a bit different. And so one of the strongest pieces of evidence we have at the moment for the existence of such a background is because the CMB measurement of this ratio is highly consistent with the standard model prediction. Okay, so we do have indirect evidence in that sense. Yeah, I mean, yeah, yeah. Set burst. Well, I mean, you can do that. The only thing is that I think I remember a PhD student in the 2003, 5. It's like Andreas Ringwald and people like that when Andreas was not doing axions. Um, they looked at this possibility, and I think trouble is that it's very hard to tell whether you're looking at a dip or whether you have two power laws. If you have one power law like that, another power law like that, it will look like a dip. So it's this sort of thing is hard. I would say in general. Yeah, 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 yeah. And actually, I think I understand that a lot of people doing dark matter these days actually started thinking about measuring relative neutrinos, and then they figured that it's just too hard. Let's do dark matter instead. Well, you're limited see, the thing is that with measuring anything standard model is that you're limited by the standard model. Measuring dark matter, you can invent anything and put a detector there and measure what you've just invented. You're not constrained by anything because you don't even know what it is. Yeah, yeah.